solution? Well, if you look at the notes, you can see the Taylor series note. Some of the things we're going to need for the Taylor series expansion. Number one, we need to come up with expressions for the nth derivative of x. So let's see if we can find a pattern for this. First, the zero derivative of x is just the function itself, the cosine of x. Before I start this, let's recall something about cosine. We know that if we take the derivative of cosine, we're going to get negative sine. That's different than cosh. If you were taking the derivative of cosh, you would just get positives, sinh. But this sine, the cosine derivative, gives you a negative sine. Also, sine x has a derivative of cosine x. And let's see. Oh, we're going to be evaluating these guys at pi. So the cosine of pi, that's equal to -1. And the sine of pi, that's equal to 0. So this is all information we'll be using in this first step. Okay, the first derivative of the cosine function is negative sine x. And the second derivative of cosine is the derivative of negative sine, so it's negative cosine x. And the third derivative of this function is positive sine x. And let's see, let's go one more. The fourth derivative of this cosine is equal to cosine x. Okay, that's all step one. Now let's go to step two. Step two says, let's find all these derivatives evaluated at a equals pi. Okay, so we've got the zeroth derivative evaluated at pi. That's the same as cosine of pi. And we see in our little recall box up there that the cosine of pi is equal to -1. The first derivative evaluated at pi is negative sine evaluated at pi, and that gives us a 0. And let's just go ahead and fill these out. The second derivative, the third derivative, the fourth derivative, at pi, equals. We had negative cosine. Pi here, we have positive sine. Pi here, we have positive cosine. Pi here, equals. Cosine, negative cosine pi is positive because it's double negative. And we get a 0 here for sine pi and a -1 for cosine. All right, now for step 3, we can apply the formula. Remember, the formula for the Taylor series is centered at some value a other than 0. If it were a Maclaurin series, we would just let a equal 0, and it would be a similar calculation. So the formula says this. It says f of x, when you expand it as a Taylor series, is equal to the integral, the sum, n equals 0 to infinity of, now here's the coefficients, the function, the nth derivative of the function, evaluated at a, which in this case will be pi, divided by the n factorial. So we're going to sum all of these times x minus the center, which is a. In a Taylor series, in a Maclaurin series, it would be just x because it's x minus 0, raised to the nth power. That is the formula we're going to apply here. We're going to let the center a equal pi, and we're going to fill in these guys. Let's actually expand this and see what it looks like. The f of x will be equal to, let's see, the first one will be the 0th derivative evaluated at pi, divided by 0 factorial, and all of that times x minus the center pi to the 0 power. Plus, now we let n equal 1, the first derivative evaluated at pi over 1 factorial, that's the coefficient, times x minus the center pi to the first power, plus the next one, let n equal 2, the second derivative evaluated at pi over 2 factorial times x minus pi to the second power, plus f3, third derivative, at pi over 3 factorial times x minus pi to the third power. I want one more. Let me squeeze one more in here. Plus f, fourth derivative, evaluated at pi over 4 factorial times x minus pi to the fourth. And of course, this is an infinite series that goes on forever. Now, let's use the values we found in step 1, well, actually step 2, and let's start simplifying this. So this is a cosine x that we're expanding here for f of x. And the first derivative, the 0 derivative, is equal to 1 when we evaluate it at pi, -1. So that we first get a -1 times x minus pi to the 0 power. Well, that's just 1, so that doesn't change. Plus f pi, the first derivative evaluated at pi over 1 factorial. Well, that first derivative was negative sine of pi, which was 0. So this is just 0. Plus, now we're up to the second derivative evaluated at pi. That was positive 1 times x minus pi to the, let's see, second power, because we're letting n equal 2 here. Let me make sure of this. Yes, n is equal to 2. Oh, and I forgot my factorial. For this one, it's 1 over 2 factorial. Okay. And then plus the next derivative gives us a 0 in step 2. And then we have plus Now we're up to n equal 4. For n equal 4, we get negative 1 over 4 factorial, because n is equal to 4 here, times x minus the center pi raised to the 4th power, plus dot, dot, dot. And you can see what's happening here. We are only keeping every other term. We have negative 1, plus we have x minus pi squared, because we skip the first power, over 2 factorial. Then we skip the 3rd power, and we go plus, actually it's minus, isn't it? So I should have written a minus. I'll put a negative 1 instead. Negative 1 over 4 factorial times x minus pi to the 4th, plus, well, you see it's alternating, minus, plus, minus, plus. So let's write this in a sum series. We've got the sum. Now we want the first term to start with n equals 0 to infinity. We want the first term to be negative 1, and we want alternating signs. So let's make that negative 1 to, well, we can't say the n power, because then it will start with a positive instead of a negative. So instead we're going to say to the n plus 1 power. That will have an alternating sign starting with a negative. And then we have, let's see, we have, of course, the x minus pi, but it's only raised to the 2 power, the 4 power, or the 0, the 2, the 4, the 6, only even powers, so 2 times n will give us even powers. And then on the bottom, we're going to have even factorials, 2n in parentheses factorial. And that's actually our answer for the Taylor expansion of the cosine. Okay, now for radius, let's see if I can squeeze this in here. For the radius, the ratio test says that the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n has to be less than 1. That's required for convergence. Okay, so we're letting a sub n be this expression right here. This is our a sub n. A sub n. So what we're looking for is, we want the limit as n approaches infinity of the absolute value of, okay, let me write this all at once. Instead of dividing by a sub n, I'm going to multiply by 1 over a sub n. And that's going to give me, let's see here, I've got x minus pi to the 2n plus 2 power when I distribute. I let n equal n plus 1, then I distribute the 2. And I also have times, well, on the bottom I have 2n plus 2. 2n plus 2 factorial. Okay, so then I multiply that by the reciprocal of a sub n, and that gives me 2n in parenthesis factorial over, let's see, parenthesis x minus pi to the 2n, and that has to be less than 1. Okay, now if I could just go really fast to simplify this. First of all, I'm going to pull out all the x's, but since I want to make sure they're non-negative, I'm going to keep each of them in absolute value bars and bring them out in front of the limits since they don't depend on n. We've got x minus pi to the 2n plus 2 minus 2n because of the factor of x minus pi, absolute value on the bottom. So you see these guys are going to cancel, and it's just going to be the second power. Times the limit as n approaches infinity. Now I do not need absolute values here. I have 2n in parentheses factorial. And what do I have to do to the bottom to get a factor out of 2n factorial? I have to go down. So I have 2n plus 2 times 2n plus 1. And the next would be 2n plus 0, so it's just 2n. I can stop there and put a factorial. And then these guys are going to cancel each other. And this has to be less than 1. So it ends up being that this is the absolute value of x minus pi squared. And I divide both sides by the limit, and I get this less than 1 over, well, 1 over what? Well, the limit as n goes to infinity of 1 over this product on the bottom, 2n plus 2 times 2n plus 1. It's going to give me 1 over infinity. 1 over infinity is 0, so this is 1 over 0. And then when I take the square root, it's the square root of infinity, which is still infinity. So we have x minus pi has to be less than infinity. And that is what we consider when we're looking at the ratio test for the Taylor series, x minus a being less than r. So that implies that my radius, r, for this Taylor expansion, r, is infinitely large. And what does it mean to have r equals infinity? All that means is that the domain for the expansion, the cosine, the domain is all real numbers. And we're finished.